We'll hit play. Okay. All right, welcome everybody. Thank you for being here for the third workshop of our series here. We're very excited to have Benjamin Dolan, who will be talking with you. I cannot think of anybody that I would say is an expert in prototyping quite as much as we can say Benjamin is. So we're very honored to have him here. Let me first share the screen and walk you through a little bit of the competition in case you're not familiar with some of it. Hopefully everyone can see that and it's not too obtrusive for them. For those of you who don't know, my name is David Ochi. I'm helping to put together this competition this year and have been a judge for probably, I think, 7 or 8 years now. And obviously been on campus for quite a bit, launching the Entrepreneur Center and involved with New Venture competition and all that. So welcome. It's a fun competition. For those of you who don't know, the competitions in terms of the distinction between the two, the Butterworth competition is focused around information computer science. The Beall competition is focused around hardware and engineering. There's a lot of overlap. The only rule is you got to pick which one you want to compete in. The ultimate goal is to promote excellence in product design and development among the students. So many of you are students here. That's great. It is open to all UCI students. So if you're from the business school or whatever, that's more than okay. You just do have to have one person from ICS or engineering on your team in order to compete in those two competitions respectively. And then of course your teams have to be made up of UCI students. The reason most of the people compete, of course, is to take home the grand prize. It's a $10,000 check. We're very excited about that. I can actually, I haven't even had a chance to create the slide on it, but there's actually a bonus prize that we'll be talking about briefly tonight. I'll maybe save that for the very end as a hook to keep you around. But there's an additional prize that you can be eligible for, but it's $10,000, $6,500 and $3,500 for first, second, and third. So between the two competitions, there's $40,000 in total cash. That actually will be $47,500 when you hear about the additional bonus prize. So real quick on due dates, if you haven't done it, I would recommend doing this. Hopefully you've done the product specification. You may note there's a slight change in that date. Some of you may bang your head against the wall and say, but I worked really hard to get it done last night. Very true. There were some technical issues. For those of you who didn't know, there was actually a Google outage that started to roll out this morning. And so we had a couple people also have problems with the website. So we've said, look, let's give you guys the rest of the week to also try to pull it together. So the template is up on the website, but we've extended the deadline to the 16th. You don't have to worry if you've already submitted. This draft does not get judged in the sense of points. So it's what you have is great. Run with it. The judges will evaluate it. We'll do a review with you on the 23rd, which we'll schedule with you soon. And so run with what you got. Don't let that stress you out. What matters is the final submission. This submission doesn't really matter in the end, right? What matters is what you do at the end. That's May 9th. We've got a final product and business case that we'll have you pull together. More details on that will be released as soon as we're done with that midpoint review and really get you focused on that. There is a template. We're going to do a slight revision, so don't get too hooked on that template. There will be a demo day, and that we will have already received your demo of your video, but there will be an additional demo day where we will have already watched those videos, but we'll really get some one-on-one time with each team as judges to really dig into the demos and understand better about what you're doing and the work that you put into it. And then of course, we'll give away lots of prizes on the 24th for an awards night. That'll be lots of fun. As much as a fun that you can have in a Zoom environment can provide you. You know, it's bring your own water is the word I'll use, or other alternative beverage. And so this one, we are moving this date, so I didn't scratch it out, but that's now going to be the 16th. And we've got a series of workshops you can see right here. We're in this land right here. And then there'll be additional workshops coming up. I won't go through the details, but the first one is that you definitely want to look at is this workshop 4 that's on the 26th. We're going to have a guy who's got a lot of experience doing product design for companies like Samsung and Western Digital and some big names, talking about product design and some of the elements they've used. And I mentioned this and I put the link into the chat. We're going to experiment with this wonder.me thing. Again, it was a fun thing to hang out and chat afterwards. So we'll experiment with that some more when we're done. It doesn't work when you're in Zoom because it requires camera and audio like you would in Zoom. So that creates conflicts, but it was a pretty effective tool for us to create little circles and enjoy some conversation. So with that, unless there are questions, which if you have a question, feel free to just unmute yourself and bring that to the forefront. I'm very excited to introduce Ben. And Ben, I have to ask you, do you prefer Ben or Benjamin?
Doesn't matter to me. I always introduce myself as Benjamin because for whatever reason, if I say, hi, my name is Ben, people are like, hey, that's great to meet you, Matt. So I always just say Benjamin, but then generally go by Ben.
Deal. Well, Benjamin has a wonderful, stellar record here. I met him probably 7 or 8 years ago when I was up at Rapid Tech going, what is all this stuff? And he has an amazing way of walking through exactly all the equipment. We have an exorbitant amount of equipment that's available for prototyping, and he can go into a lot more of those details, but he's got a keen eye for prototyping and the process that we go through to really build out prototypes. You remember our speaker last week was talking about low fidelity and high fidelity prototypes. When you really are ready to make that jump into the high fidelity prototypes, or at least a mid fidelity, right? Benjamin's really, he's a huge asset for you guys. So with that, I will stop my share and let's all give a virtual round of applause to Benjamin for our next speaker for this workshop. Thank you, Benjamin.
Sure. So yeah, I'll try to keep the kind of PowerPoint thing shortish, just so you can see a bunch of photos of sort of what sort of things these things can make. And I'm not going to claim they're great examples. These are a lot of student projects that have been left behind and things like that. And then we'll walk through the lab so you get an idea of the sense of scale of the machines and how they work. And then please, at any point, feel free to interrupt. If you're going to do it, and you can, do it by audio, because if I'm sharing the screen, sometimes it's hard to see the chat window on this computer. But yeah, let me go ahead and share this real quickly. And we'll see what we get. What? Okay. It's giving me a warning here that it's freaking out. Are you able to see a table of contents at the moment? Yes, okay, I see a thumbs up. Okay. All right, so we're gonna go through here. We've been around a while. I've been on campus here since 2010-ish, but we started out in 2004 at the community college as a National Science Foundation Center. Helped hundreds of companies, trained tens of thousands of people sort of thing. If you look at the impact that you can have at one training event by training all the trainers. Yeah, we've been around a while. So past people, a lot of big names, a lot of the alphabet soup of our government, like the DOJ and FBI, CIA, that sort of teams, local companies as well, medical, automotive, doesn't really matter. Because the thing to remember is any of this additive stuff is just another tool, okay? Doesn't have to be for one thing. The machines don't know what they're making. That's up to you to be creative and get these things to do what they're doing. We'll skip this stuff. Basically, this used to be called rapid prototyping or 3D printing. And the industry said, nah, you know what? That all sounds like it never gets past the beginning. We want to do additive manufacturing. And what's the difference? There's no difference. It's just additive manufacturing sounds like it puts out real parts, because it actually does. All of you have presumably traveled on commercial air. Pretty much guarantee you that aircraft had additively manufactured parts on it at this point. It's on cars, it's possibly in your body, depending on where you've had your surgeries. If you ever had Invisalign, that's all additive manufacturing. So it's definitely around us now, and it is a real thing. So the big yays, doesn't care about how complex your shapes are. If you got things set up right, there's basically no machine setup or tooling, which means you hit the big green button and hopefully it prints your part. You can do composites, and that means not just things like carbon fiber and Kevlar, but you can mix plastics and rubbers together to get squishy parts with firm parts and all sorts of stuff. Here goes my lights. Freeform fabrication means you can do weird shapes, you know, and you can do them in any orientation basically. So if you wanted to do statues, that's cool. The big benefits, go, no go. So this is one of the places where you'll probably use this. You print it out and you say, yep, let's go with that. Nope, let's stop. Visual communication, it's what I'm gonna try and fail at a lot tonight, which is showing you stuff, conveying the idea. Demonstration, does it do the thing? Form test, does it look right? I don't know how many parts I've seen people print out that they thought looked awesome on screen, and then they put it in their hand and are just like, what in the world was I thinking? So the form is extremely important. Fit, of course, does it fit where you need it to? Function, does it work? And then business communication tool. We'll see a couple examples of that, but trying to convey ideas to your clientele. So there are only 7 major technologies that you got to know. And this was there, I mean, there's hundreds of names out there, but when you break them all down, they generally fit into these 7 categories. So you got vat photopolymerization, material extrusion, binder jetting, powder bed fusion, material jetting, directed energy deposition, and sheet lamination. Of these, UCI has 6 on campus. Maybe 7 if there's one hidden. I'm not sure about where sheet lamination would be, but all the others, I know where they are. And 5 of them are, you'll see tonight. So we'll skip these. Outside of the 3D printing, there's a host of other things that are great for getting prototypes out. And that includes casting. So this could be using vacuum chambers and pressure pots to make rubber and urethane plastics. Furnaces, spin casting, vacuum investment, sand casting if you're going to do metal components. This is used a lot in jewelry and automotive and aerospace. General fabrication stuff, CNC machining, welding, wood shop tools, composites, laser cutting is huge, great for making flat stuff fast. And then a boatload of software to do all sorts of specialized things. We'll see some of that tonight. So the whole thing, these 6-ish steps are how you get a part. So create that 3D file. It doesn't matter what you make it in. For us, most of the time it's SolidWorks, but you know, you could be using AutoCAD or Fusion 360, Inventor, some virtual clay sculpting software, FreeCAD, doesn't matter. Create something and then convert that thing to an STL. So this STL file is the universal 3D printing file. All right. It's been around forever. It's not perfect, but everybody can work with it. So that's the cool thing. You got to check that file for problems because it is an approximation of your original. It converts every shape in there just to triangles. So you got to make sure it did so well. And then you load it into the machine specific software and you slice it for that machine. Send that slice file to the machine, hit print and wait. And if everything goes well, you take the part out and do whatever post-processing you need. So this could be sanding, removing support, painting, just cleaning it, who knows? All right. So I'm going to go through this stuff really quickly because we'll discuss it while we're in the class. Vat photopolymerization, stuff's been around since the 1980s, commercialized by a monster company called 3D Systems in '87. So this thing uses a laser or some form of light, could be from a projector, to cure a big vat, a bucket, if you will, of photopolymer. So this liquid is light sensitive, and when the light hits it, it turns to a solid. And it's used a lot in the real world for making hearing aid shells and medical models, general plastic parts. You can do waxes, some rubbers. It's getting there. Weird stuff, but it's getting there. 2 versions of it. There's one where light shoots down into a big, deep vat, and it only operates at the top level. And then what we've seen more of recently, if you've seen any of the Form Labs machines, this version has a light source below a tank. It's a little tiny tank, and it peels the parts out of that tank so that they hang upside down like a vat. Uses a lot less material, which is nice because that material is expensive. Has some peculiarities, but we'll go on with that. So a few examples. General PPE there in the middle, students wearing safety gear. You got gloves, safety eyeglass stuff, lab coat. That material smelled horrendously. I'm glad I've lost my sense of smell, but that was awful. But you can see it's a very thin little tray that Tom there is using. It's about 1 inch tall, but you can see that this kind of greenish bluish glass, that's how tall of a part you can build. So it's quite a bit taller than that tray would let you believe. Things around, little lattice structure sitting on top of a penny there. This is a medical device that held probes against the surface of your head to detect migraines or something like that. I forget what they were measuring. But both the mold, the tool, and this inside part in the caps were printed. And then this outside part is silicone that was overcast or cast over those parts suspended in the middle. That way it was the silicone that was touching you and not that 3D printed part. Other lattices, mock-ups of brake and caliper, probe holders again. This is a skull we'll see part of. This structure here, these fine kind of waterfall looking things, are a support structure to hold that all up. Functional parts, this is the inside of a motorcycle. This is a rebreather valve that actually raced at Daytona. Some communication devices, little tiny probes. These things went inside of the lung. These are fiber optic cables. You can see those are 6 of them sitting next to a penny. Now, that material itself was not rated to do it, to be actually used in that way, but it was just the prototype. Originally, they would be converted into steel or something like that. The big one that people are generally familiar with is material extrusion. These are glorified hot glue guns. This was developed in the late 80s, commercialized in the 90s by Stratasys. This is Fuse Deposition Modeling was the trade name from Stratasys. They're cool in that they use real materials in terms of thermoplastics that you've probably heard of, like ABS or polycarbonate, nylon, things along those lines. And thermoplastics are neat because you take a material, you heat it up, you change its shape, and when it cools, it's that new shape. So let's see, there we go. These are what you see as all the little MakerBot machines. You can buy them for like a couple $100 from Amazon at this point. You buy spools of the filament, looks like weed whacker wire. The commercial machines can be far more impressive. I mean, you're looking at hundreds of thousands to maybe $1 million for some of the big stuff. Very popular because it's really, really easy to use. Okay. So weird research shapes. The devices in the middle were made for our urology department to train for laparoscopic surgery. Put an iPad on that thing and practice stitching people up from the inside, removing kidney stones and stuff like that. Weird flexible joints. You can print plastic, rubber, plastic if you got multiple parts. Art/architecture things. Third world malarial testing devices made by grad students, all sorts of stuff, quads. Binder jetting, this is used a lot in industry, but typically not in a way that you would see. So this started out as 3D printing out of MIT in '93 and was commercialized by Z Corp, which has since been bought by 3D Systems. So where it's used in the real world is printing refractory sand for doing sand casting of things like engine blocks, cylinder heads. stuff along those lines. Great for statues. You can print in plastics. You can print in metals that get sintered. You can do weird stuff like print in sugar or ceramics, all sorts of things. And basically what you're doing is you're laying glue down on a bunch of powder and printing your part that way. So advantages: on ceramic-based machines, you can have full color models. So this would be one of the business communication tools. So example here, this was from a company down in San Diego that was producing constant variable transmission bicycle hubs, and they wanted a way to describe what was inside, but they couldn't cut one apart without it exploding into a million pieces. So they sent us their assemblies and we printed it and glued it all together in this cross-sectional view so that they could show people, hey, when this thing spins, these little orange balls move in this way and it causes increased friction and whatever. It's great for medical. This little infant skull there is from CT or MRI data. You can, as this example on the top left shows, pour metal directly into these things and get out, bronze or aluminum or whatever you need, as long as the temp's not too darn high. So in that case, they're actually pouring a putter head that was just absolutely miserable, but we've used this for cylinder heads and things like that elsewhere as well. Next up is powder bed fusion. This was a DARPA project in the 1980s out of UT Austin. And powder bed fusion relies on some sort of high energy source, typically a laser or electron beam. Sometimes it will be just really intense lights to fuse a powdered material. And this could be plastic or it could be metal. Kind of depends on what you're going for. On the plastic side, we're working with things like nylon, polystyrene, loaded materials. So you could have some plastic with glass or carbon fiber in there. It doesn't matter, as long as it's within the temperature range of that machine. And then on the metal side, your typical ones of 316 stainless or some of the aluminum alloys. You can do Inconel and titanium, gold. Depends how much money you have, honestly. Those machines are expensive and the material is really expensive, but used very much in the real world. Rocketry, defense, medical, automotive, it's out there and really makes real stuff. This is an example of one of those technologies. This is SLS, which was selective laser sintering. And it shows a little laser bouncing off a mirror and shooting down into a bunch of powder. And the deal is the powder is generally heated, and that laser gives it enough energy to melt locally to its nearest neighbor. When it's done, a big roller comes over and basically squeegees a new layer of powder across, and it repeats. So when you're done, you dig all your parts out of powder. So places it's used, if you've flown on any of the big Boeing planes that have the GE LEAP engine in it, you had 3D printed parts in the engine. If you've had a hip replacement or something like that, that's what that top left image is. So that's an acetabular cup. The outside is purposely printed really rough, and the inside is smooth and then machined to get even smoother. But you can print parts that fit you and only you. So if you've got a slight asymmetry, or let's say you've got some degeneration or something around the joint, you can print it so that it fits you perfectly. In the middle, there are some thing that's pretty mundane. These are little bolt covers for lampposts in Washington, DC. The original ones were all cast and were getting stolen and rotting away. And so they had us laser scan some originals and then recreate the tooling in order to make them so that they could continue to have this part of the history around DC. Math model there, this came out of Santa Cruz, some sort of tessellated surface. And this top right picture is a melted layer as it was recently melted. And it's bonding to its partner below. And once you dig it out, you can see It's all just loose powder sitting around. Material jetting is one that you have almost certainly seen because Hollywood loves material jetting. So if you've seen any of the big Marvel movies that had Iron Man, his costume was 3D printed when it wasn't animated. Okay, so big ones here are 3D Systems and Objet. Objet is partnered with Stratasys, 3D Systems is its own. And this uses an inkjet-like head, and it deposits little droplets of material. And those are either photo cured or just left to cool. And you can do plastics and waxes and rubbers and clear stuff, medical stuff, dental stuff. It's kind of all over the place. So an example of waxes, investment casting, you can print jewelry or badges, hammers, whatever you want to turn into a highly precise metal piece in a traditional way. So we had student owned a drum company, decided to make his own badges, drew them up on a cocktail napkin, and I converted those to 3 dimensions, printed them out in wax, and then he had them investment cast into bronze. Medical devices in the middle. This is a breast cancer detection system, just the housing for it, for our own Beckman laser here on campus. Little silicone molds. Architecture. For scale, this is Casino Morongo. This little printed model here out of plastic, that's a 1/2 inch. So fairly fine detail. And this was done ages ago in order to help convince people that it was a cool shape. They were having trouble seeing it in 2D images, so they wanted a little 3-dimensional one that they could put on a desk. Some car parts. Directed energy deposition, late 90s, kind of new to the game. This one is pretty rad. I don't have this in my lab, but it is in another lab here on campus. And this uses powdered metal and it blows it into a laser beam and it heats it up really quickly and it sticks to another part. So in industry, it's used a lot to repair really expensive stuff. So like you've had an impeller fail and maybe it was hundreds of thousands of dollars to machine that thing. You don't want to just scrap it, you want to repair it. So you could stick this thing on the end of a robot and it's going to blow the metal just where you need it. And then you go back and machine just that section. Used a lot in defense and things along those lines where you have high value parts. On campus, the research is a lot into the materials. How do we make really interesting materials that you wouldn't typically dare print on another machine? And then lastly is sheet lamination. So this puppy, you don't see much of it anymore, but it's still there for really big stuff. So you take a sheet of something, and that could be plastic or paper or metal, and you bond it to another one and you cut out the layer that you want. So for big metal parts, this can do neat things because you have just these giant rolls of material that can do, an 8-foot by 40-foot piece or something like that. They tried to do it a lot in schools because you could actually load just a ream of printer paper into these machines. And it would, instead of printing ink, just print glue, bond them together, and you could get these paper parts that were really low cost, which was attractive. So one of the things, enough of those, we're going to go take a look at some of those now, but other things that are important for this stuff, that's not necessarily just producing a prototype. You can use it to create lightweight tooling and fixturing to reduce workplace injury. So, let's say you're an aerospace manufacturer and you got to rivet the skins onto your plane still, and it's done by humans because it's low volume. Well, you don't want somebody lifting up, an 80-pound drill template over and over again, especially if they could drop that onto a wing. You want to print a hollow one out of plastic. And if you have a design change, you just print a new one. Now they're carrying a 10-pound, part, and they can still, you put inserts in and sleeve it and it'll drill all day. Custom work holdings and jigs that are brutal to make. You know, you're doing plumbing, or you're putting badges on a car and you want it to be in the right place every time. Make it ergonomic. You know, it's easy. Find the person that you want, figure out what their hands look like, hit print. It'll reduce workplace injury, for instance. Prototype and bridge tooling. This is, let's say you're a major manufacturer of automotive parts and you've had a recall. You've got an oil pan that isn't working right. Well, you can prototype those tools that are necessary to make that oil pan before you go to your hard tooling to make them. So you can 3D print that sand core and cast a few, make sure everything works right this time before you go and commit to the commercial tooling that might take months to machine. You can kind of stem the bleeding, for instance. Making mold masters for silicone and urethane tooling. This is Hollywood all over the place. But it's also awesome for medical use. So if you're doing prosthetics, this is great. Creating patterns for traditional sand casting, already kind of touched on that. Masters for investment casting, huge in the jewelry industry, right? You can do some crazy shapes on a computer that would be hard to do by hand. So you hit print, make this nutso shape, and then investment cast it. Also works great for, you know, defense, for whoever, high-end, really precise stuff. Creating replicas of expensive or fragile things that need to be handled frequently. This is your museums. Okay, we've done all sorts of parts for museums where they don't want the real thing on display. And if you've got somebody that's competent, they can make it look like that original, even though it's just made out of, you know, some additively manufactured plastic part. You could also use it, let's say you have a bunch of students that need to build something that holds a iPad, I don't know, a CubeSat or something. Well, you don't want them dropping it on the floor over and over again. You keep replacing glass, so you print out a dummy and they can beat that thing all up, and when the time comes, you put it in the real thing. And then lastly is creating parts with additive in mind. So these are shapes that you couldn't do elsewise, all sorts of optimizations and lattices. You can make some wild parts. And we'll see what we can get. All right, so I'm going to bounce out of that. We're going to switch cameras and go take a look at what we got around. If I haven't locked myself out.
That's always fun.
Yeah. All right.
Try switching the speaker view also. It might help for those of you that are that see little boxes for the video on the top right of Zoom.
So if you don't know where we are on the 4th floor of the engineering tower. We also have control over the machine shop, the weld shop, and then our FabWorks facility, which is over in Cal IT 2. So starting on the low end of things, I'm never going to knock this place, but this is what we call our dirty lab. And this is where we do woodwork. So a lot of times we're making mold boxes, we're making masters for packaging. If we want to do vacuum forming, you see here. So this was a device a student made. You blow into this part and it takes your stinky breath and shoves it back up your nose. So you can see if you've got bad breath. The thing that looks like a dog bowl is actually the liner for a spin caster in a clean room. It was made, I used a piece of cardboard and a Sharpie and some scissors to trace out the inside of their machine. Came back in SolidWorks and made the darn part. Machined it out, sucked it down. It cost like it's $1 of plastic. They wanted to 3D print it originally and it would have been several $100s. So that's made on something like a vacuum former here. And then again, table saws, band saws, This thing is a, what is that called? Pressure chamber for doing molding. So it really depends what we're trying to do. This way. All right. All right, my connection's lagging pretty hard. I want to make sure you guys can still see me.
So far, so good.
Okay. A laser cutter and engraver is super duper useful for making flat stuff quickly. So when we were supporting the COVID effort, we made thousands upon thousands of face masks on that thing. This machine is a material jet, and I'll show you some of these parts here in a second. This is what would make the Iron Man costume. So the box over on this side is where the materials go, and it uses a big head here, and each of these is a different head that can put out materials. So it's putting little tiny droplets of material on. So you can create, really fine structures like this. But of interest is a project like this will take rubber components. I don't know if you can see that I'm deforming that, and plastic, and print them simultaneously. So you can have sections that are very, very flexible and other sections that are perfectly rigid. And interestingly, this is unfortunately something you'd have to be here to feel, but you can change the stiffness by blending the rubber and the plastic together. So on a scale of 100, this is a 30, and let's say this is 100, you can go 30, 40, 50, 60, 75, 85, 95, and have a gradient if you wanted it. Products like this were based off of laser scans, printed, sanded, and painted to give a nicer finish. This is part of that breast cancer detection system. The bigger brothers of these machines now print in a crazy amount of colors. So this version, you would load in 3 colors at a time, and you get one of those triangular palettes. The new versions will do 8 colors at a time and a complete gradient, like photorealistic printing. About $250,000 for the basic machine. So not giving it away. This used to be my office. I'll try to back up so we can actually see it. This is the opposite of a refrigerator. This is a material extrusion device, commercial system used by Boeing and pretty much all the major manufacturers of automotive stuff. The materials are loaded in these big spools and then fed up through the machine into this heated chamber. So for reference, this is about 16 inches across, 15 and 14. Right now we're running polycarbonate in it, but it can run things like Ultem or ABS, static dissipative stuff, medical grade materials, flight certifiable things. And it's, again, just a hot glue gun. So let's see if this will focus again. There we go. It does have a soluble support system. So you can build things. This is all printed as one piece. Kind of just a cute little toy that they like showing. So when it prints, you'll have your part like this with this brown material. And then that brown material can dissolve away in a special tank to give you your full detailed part. So some of you, if you've ever used a Dremel tool, may recognize this shape. This was a prototype for Dremel at one point. Architecture model. This whole interior cavity would have been filled with that support material. Stuff like that. Nice things, you do have control over the density of the inside. So if you want things faster or lighter, you use less infill. If you want it stronger, you can make them solid. In terms of products, a while back, one of the ones we did, I can't remember if it was for this competition or not, child tracking bracelets for theme parks. So they had figured out the electronics, but needed a way to house it. So the idea was, how do we GPS track our kids so they don't get lost at Disneyland? Silicone mold making, hugely important. If you got to make a number of things and you don't have the principal material, you make one and then you make as many copies as you need. So for instance, this goofy little propeller blade, we had students that needed a couple dozen of them and they didn't want to sand every one. So you sand one, make a mold of it, and then inject the material into this. So every one that comes out like they were already sanded. I'm getting dangerously close to out of battery for some reason. We're chewing through it. All right. So there is a 3D printer club for students on campus under normal circumstances. We did talk about machining. This is a large, but not metals. Used a lot for doing tooling. So this is foam tooling, how to make a composite part. Start with a block of foam, machine it, sand it, paint it, fiberglass tool, composite tool, finished part. So right now that one's used a lot by our race car teams and things like that. And the metals shop handles the big stuff down below in the basement. All right. So this is the classroom. Wake this computer up. The silver box and the red box are both laser scanners. So they're used for duplicating the objects you put in front of them. So if you want an anatomically correct hand, for instance, you can cast one and then laser scan it. So that's what that hand's doing there. On screen, this might be tough to see. This is medical studies. So we've got a kidney and this white spot there, kidneys don't have bones. That is giant kidney stone. So one thing that we do is help them image where these stones are so that they can plan for the surgery. Right. So you can see that that stone is filled in a good portion of the inside of that kidney. As we move along, anything you see with an orange lid, so those two machines, those three back there, two over there, three over there, those are vat photopolymerization. So those are using light to cure that plastic. So in this case, the light source is down below, and they project up in order to cure your hanging parts. So if we zoom in, let's see if the camera can catch up. Not very well, so we're exposed. High detail stuff. See if we can do a black one. a red one. Maybe that'll show up a little better. So these would be used a lot for small devices or investment casting. Like I said, jewelry is big. This was part of a research project where they needed to hold like brain tissue of rodents. So they built these little tiny structures so that they could image them. The 4 machines along this table are all material extrusion. So just like the hot glue gun machine, just different qualities. The 2 on the end to the right are more of your rough draft. The black one in the middle has a bigger platform and more options to print with. The little white one is higher resolution. You'll see that over at the Cove as well. Here's an example of some colored parts made on a binder jet. These are just kind of weird. We'll normally use this for metallic components or medical stuff. So this is, for instance, the airway of an infant child. They needed us to build models of that, and we made rubber babies around them so that they could practice driving cameras down the airway without harming any actual children. And again, vat photopolymerization machine. Let's scoot this way. So this machine 3D prints in metal. Currently it's doing research for aluminums. Previously it was stainless steel. And this is an example of powder bed fusion. So you can see the bottle at the top, that's where the metal goes and it falls down through gravity. And there's a 400-watt fiber laser in there that will melt that metal when it hits the platform. So the platforms are these solid pieces of metal. And the structures actually get welded directly to the platform and built up from there. So you can get these really complex shapes like this, all 3D printed. And they're used for lightweighting things or just building novel shapes. All sorts of stuff. And real world use. Some of these machines are much, much bigger. We're talking printing parts, meters across if you've got lots and lots of money. I was at an aerospace manufacturer that was doing that, and they were putting $40 million worth of powder into the machine before hitting print. This last room is a partnership between us and a company called Ceratec in Lake Forest, who sells this equipment. So HP is the same HP that you've probably experienced before. This is another powder bed system, but it prints by using light to melt the powder. So this is a production ready system. Let's see if I can open it. Locked. Big guy. There we go. So you can see all the heating elements. And as you would expect of HP, there are some print heads over there. And when this thing comes across, it deposits black ink onto white powder. The black ink absorbs more of that energy and causes it to heat up and melt. That's how you get your really interesting parts. So as I said, designed for production, for putting out thousands and thousands of parts. Their goal was to take money from the injection molders. And what they can do is, that's all one piece. You can nest these parts inside so that you can get way higher part density for way greater speed than the other machines typically. The downside is this is your color. It's like Ford in the beginning, you can have any color you want as long as it's black. They do have versions that now print in color, but they're not the production machines. They're strictly prototype-based machines. Now the material is where the business is. This is nylon 12. They also do nylon 11 and some glass-filled stuff. Great for really durable, strong parts, orthotics, wear items, any number of things. It's cool material. And it's expanding too. They have plastics, like polypropylene and some rubbers now as well. Then backing way up, this one is another material extrusion machine, except it does parts that are 1 meter or 3 feet by 1/2 meter by 1/2 meter, so big stuff. And it does it coarsely, that way you can still get it in a reasonable amount of time. The last machine for today, this little guy, this is a Mark Forged Mark II, and it's unique in that it can print in composites. So if you need carbon fiber or Kevlar or fiberglass and nylon, that's the sort of stuff it can do for you. All right. So I'm going to scurry back to my office so I can plug this thing in, and I will answer any questions you might have before handing it back over to David.
While you're doing that, I have to say, it's amazing what you've got in terms of equipment and the opportunities for use. So I'll let anyone ask any questions if you have some while Benjamin's getting set back up in his office. Does anyone have any questions they want to bring up?
Actually, I do have a question, and I guess it's I'm not going to say the elephant in the room, but more like the question I think is on everyone's mind here, which is how, if we wanted to gain access to these facilities, what will be the process?
So you can't at this point. It's getting more open, but in general, this facility is designed for me to do stuff for you. Our FabWorks site is designed for you guys to do it yourself, but due to the costs and training requirements for using most of this equipment, I work more as an internal service bureau. So the easiest way is if you basically email me what you want to build, and I help you figure out if we can do it.
And at what point is it good for that to happen, right? Should they have already done CAD drawings? Should they have a really crude prototype they've made with, dominoes and rubber bands in their dorm? Like, at what point is it right to send Benjamin an email?
Well, yeah, that's a great question. It kind of depends on the project. So if you have somebody that's already done your CAD model, that's fantastic. So there's a very good chance I can work directly from that. If you don't have anybody on your team that can do the 3D modeling, then you can share your idea of your glued together dominoes. And I can look at, okay, how much effort is it going to take to convert that to something that we can print from? So it will depend on you. It's certainly cheaper if you already have printable files, because then I'm not taking the time to create everything for you. But in the past, some teams have said, nope, we hired the computer science guy, he did the programming, somebody else needs to figure out how to do, the enclosures or something.
Very good.
Yeah.
Other questions? I'll maybe ask a question about pricing. Like, how does that work? I mean, your time and the equipment can't be cheap, but like, what are ballparks of
So
know something.
each machine bills at a different rate. And essentially we just look at cost recovery. So, you send this part and I'm going to look at the part and try to understand what it is that you're doing. I'll discuss that with you. So we're looking at, okay, are you just trying to get the general shape down? Are you going to abuse this? Is it, you're going for fidelity? What are you trying to do? And that will kind of help me figure out which, if any of our machines are suitable. And then I'll discuss pricing with you based off of your specific geometry. Because depending on the orientation that you print, the same part can have wildly different costs depending on kind of what you emphasize. So it's always hard to give ballpark for some of these things. But they can range from, $4 for the cheapest part to hundreds of dollars. Because some of the things that I've seen sent to me will take literal days worth of continuous printing. And at, $45 an hour or something like that, that would get expensive fast.
Yeah. So is anyone on the call, by the way, planning on doing some sort of 3D printing or additive manufacturing to create prototypes along the way? Because not everyone's got has a hardware component necessarily to what they're doing, but in particular for the people on the call, is there anyone that's doing something that does involve 3D printing?
We're not sure on ours. We've been thinking about it, but it's one of those you kind of learn about 3D printing more and more and then understand if it's something we can use. We've talked to Ben a little bit, which is cool. But we started with the smaller part and we pivoted to something much larger. So it's kind of understanding what can be done, learning a lot about it, but yeah, we're still not sure if 3D printing might be a way we can go.
And so along those lines, I'm never going to be the person that tells you you should 3D print something if I don't think you should 3D print something. It never benefits me to build something useless. If it's not the right tool for it, I'm going to tell you that. We're not a profit center. So me billing out garbage parts makes no sense. I don't want to waste my time. I don't want to waste your time. So if you guys have a question, and this goes for any of the teams on the call or that are watching this after, like, hey, does it make sense to do this? I'm going to give you my opinion of that. And I have no problem turning you away. And if I do, I'll try to point you towards somebody that I think that could help you if I know somebody. But yeah, don't feel like I'm here to sell you this idea. We're just another tool for you. Okay.
So one thing that comes up obviously is, how can a student buy time from on the machines directly from you? Then is there a way to actually bill through on that?
Yeah. So we have a payment portal that will take a credit or debit card, and then in the future, if you're ever on a project that has a set aside pile of money through the campus, we can take campus money as well.
So one of the things I'll mention that I don't know if Benjamin, I mentioned it to you, but I'll mention it to everyone on the call here. If a team is looking for some 3D printing and there are expenses that you need, right, for prototyping and that sort of thing, I've been told we can find some budget. It's probably not a lot, but it's some budget to be able to pay for prototyping. Right. And so if there's a particular need, if you want to run, for example, Eric, you say, hey, Benjamin, take a look at what we're doing. Is this something that there's value to us doing it? And Benjamin says, hey, shrunk models are still valuable if they're letting you, understand the model better, right? Or giving you, visual aspects or fitment or whatever it might be that you could be creating value. But budget becomes a concern, right? Then it's just let me know. And we have that internal billing capability. I'll run it through the powers that be and get a quick approval on it. And then you'll have access to be able to do it through, through whatever Benjamin's doing or whatever the need is, right? So Don't let budget, I mean, we don't have an unlimited budget, but if there's some money that's needed to get through some of the prototyping, we don't want to let, a budget be the issue. I'd rather it be a learning experience and Benjamin, taking you through and saying, okay, look, here's what I think is best to do and here's how we'll do it. And provide that. I would much rather see that happen than let the budget be the issue. So that'll be good. And Benjamin's well worth the time.
I think so.
Yeah. Good. Any other questions?
Yeah, I've got a question, Benjamin. This is John Rao. I work for David. I bring in coffee and beer and so on.
Nice.
But no, I work a
John,
lot
if
with
that's your
inventors.
role, you suck at it because last time you brought me a beer.
Well, that's an IOU. Okay.
Fair
But,
enough.
no, I'm not. If I'm a student, I'm one of the old students. But I work a lot with inventors that are tinkering around at home and working on stuff in the garage and so on. So to make a long story short, are you open to students only, or outsiders can come see you as well?
We can do outside stuff as well. Primarily, we're pushing, if they wanted to do stuff on their own, that would be through Fabrics. Fabrics has been closed for the last year due to staffing concerns because they're student run. But yeah, I can still work with outside people, and we just got approval in this last week to have people inside the building again. So now I've got a little bit more flexibility. We're still not really open for drop-in stuff due to the constraints that are on us, but if we can set up appointments, that's fine.
Okay.
I would imagine though, you've been getting orders and work projects through digital means. I mean, now everything's done so much digitally. Have you found that to be a difficult shift? Because there seems like, part of why you additive manufacture things is to get the touch and feel, right?
Yeah.
To feel the gradients of rubber to plastic kind of thing. Have you been able to accommodate that pretty well?
Yeah, we've certainly tried. There are some things where, you are trying to describe what something feels. And, sometimes I'll put it in a box and just put it in a dead drop and say, hey, go pick this thing up at that time and put it back at this time. But, a lot of it, because it is based off of computer files, that does help. So, we can do a screen share and I can take over your mouse and say, okay, see this part? Like, that's where I have my concerns. And that sort of thing has worked well. There have been some growing pains, but we're making do.
I would imagine. Good. Other questions for Benjamin?
Yeah. Oh, go ahead.
Sorry.
Okay, I guess I'll go first. My product is not a physical product, but I just thought it was very interesting to see you step through all the different materials.
Mhm.
So I just kind of two kind of questions. And the first question is going to be what the traditional printing, the traditional process of like printing parts, I guess it depends. It's been like using molds, right? Like the way that the most commonly like used consumer goods are made is by molding stuff, or is it slowly phasing into 3D printing? And when does it make sense to 3D print instead of like casting a mold and doing it like that way? Because 3D printing is really cool, but what I've noticed is just the printers and the materials are quite expensive and it takes time. So how do we know if I was to start a company like that, how would I know, why don't we just, spend $10,000 and cast a mold and just, like throw in some plastic in an assembly line? When would that be better or worse?
So the big part there is figuring out what your market needs, right? So
Yeah.
If you're making a iPhone cover, injection mold all day, no doubt, right? You need millions of objects at a low cost. You're not going to be injection molding with any sort of additive manufacturing. Now, I gave the example of like the Invisalign thing. Okay, relatively high value, and every one of them has to be different. That's 3D printing. Okay. Another example, I have done work for a automotive restoration shop. that works on vintage Ferraris. These are $12 million cars. They are one of one or one of two. There are no spares, right? And so if I need to make parts for those, doesn't matter what that cost is, you're going to make it.
Okay.
So on consumer goods, it's high value stuff or mass customization so far. We're getting a little closer towards low volume runs with things like that big HP machine. But yeah, because of the kind of linear nature of a lot of these things, it doesn't usually make sense. But jewelry, things where you want to be able to change stuff and have a lot of individual, that's where it makes more sense.
So kind of like things that are kind of going to be unique or kind of like prototypes would be better for 3D printing. Can you guys also print molds for injection molding, or is that not possible with a 3D printer?
You can. Whether or not you should is so, you know, if you are, so bridge tooling or prototype tooling, you can print in a high temp plastic and then shoot, you know, polyethylene or something into it, a relatively lower temperature material. The thing about injection molds in general is they all have to be, you know, relatively simple shapes, because you have to follow rules of draft and things. You can't have nested components that you can't pull apart back out of. So it doesn't necessarily take advantage of a lot of the shapes and complexity that 3D printing can do. But that those little covers for the light posts in DC, that was a printed metal mold because it was a really organic shape. And we purposely kept all the flaws in it, the texture of the originals. As one of them had like a dent where somebody had dropped it, things like that. And the reason was when they injection molded it, they wanted it to look like it was a 200-year-old piece of junk, right?
Yeah.
They wanted that nice texture, and you wouldn't machine that in. You would see your tool marks, or you would end up polishing it out and you would see that. Versus in a printed form, like, oh, okay, yeah, it's just an old piece of stuff. Who cares?
That's cool though. I just had to wonder, you know, because I'd always been interested in it, and I'd looked up pricing, and I was just like, man, like that sounds, that sounds expensive. So I just wanted to ask, you know, like that's why I wanted to know, like, you know, what is it right and what is it wrong? Because like in my mind, I was like, well, 3D printing is like, you know, it's super popular today, but like in the back of my mind, I was also thinking, so then why are these companies all, you know, using injection molding when they're mass producing this stuff? And that I think really helps clear it up, just so that I know the difference. And my other question was just about kind of like what's the strongest material that you can print? I mean, obviously you have metals too, but I know you guys probably, I know the Mark Forge used to print, I think it used to print carbon fiber, or maybe that was a different.
It does, yeah.
And maybe that was a different printer, but what are the most durable materials that are printable? Is it the metal ones, or is it going to be like
so,
like
you know,
plastics?
No, it's definitely the metals. Metals are nasty to work with. Those machines are just miserable. But you've heard of the black box in an airplane. So that is Inconel. And that machine that you saw tonight prints an Inconel.
Really?
Yeah.
That's crazy.
So, I mean, super high temperature nickel based alloys, they're nuts. On the plastic sides, you have nylons and like the carbon fibers and things like that.
How do you guys get these machines in there? Some of these machines look bigger than the door. Do you have somebody like assemble it like inside?
Yeah, a number of them do come in multiple parts, and you have to assemble it when it gets here. You know, it takes 3 trips up in the elevator sort of thing. Some of them we actually can't get back out of the rooms because they're taller than the doors.
I know, that's what I was thinking. I was just like, there's like all these huge printers, and how does the electricity even work in this building? Does it just like each floor must draw like how much? I don't know what it is, but it must be crazy. You must have some kind of complicated like setup, right? Do you have like special electricity for like, do you have like 240-volt like plugs or something like that in the?
There are some serious power concerns. Yeah.
So it's not just a regular AC outlet. It's got like a special like.
And that's one of the old buildings too.
Yeah.
mean, in a
I know,
newer
that's what I was
building,
thinking, right? Like I was
you
just
know,
like, this is
this was
even one of the
40
newer
years ago or
buildings.
whatever.
Yeah.
It's pretty
one of the-
crazy.
One of the earliest buildings on campus. So,
Yeah.
Yeah, which makes it even crazier that you guys were able to retrofit it to handle like, because I'm sure when it was built, like I'm sure they had some idea that it was going to be used for engineering, but like the amount of just power and like equipment that's on each floor is it's crazy to think about.
Well,
I think
at least back then, the computer took up the whole room.
I know, right? It'd be worse if it was
It
smaller.
was probably designed with the computers in mind, right?
Yeah.
Floor size computing. And
Yeah.
those
Yeah.
things had a lot of power as well.
There's
Yeah.
I mean, there's literally a crane on the side of this building, and the side of the building opens up because they used to have to hoist the
I've
computer.
seen that before. I've seen that before. Like you can see them moving the stuff into the building. I was like, that's crazy. Like that's just crazy. That's so cool. Well,
Yeah,
very cool.
Okay. Well, thank you so much for the information. It was really cool to see all your cool stuff. I'll definitely keep that wisdom in mind for the future. I appreciate that.
Glad we could help.
Benjamin, are you willing to share the slides so people can go back and look at some of those, some of the details of those lists and everything?
Potentially. Yeah, I think I have one that we can let out.
Okay. Anything that gives them a guidance, the different types of machines, and I mean, whatever you have, that would be great.
Sure.
Any final questions before we head over to some networking? Eric, yeah.
I had a quick question about the body scan.
Mhm.
So for like FX or special effects work and like art stuff, do you ever collab with artists or students that are in the art school?
Yep.
So I'm interested in like body molds for fashion work. I was kind of wondering, and this could go down a hole, but like, how much does it kind of cost to build a mold? Generally, is it really, really, really expensive, or just like really expensive?
I see. Yeah, that depends. So, the cheapest way to do it is probably a bucket and some alginate. So if you ever had braces or something, alginate's the stuff they stick in your mouth to take the mold of your mouth. It's ground up seaweed and some other stuff. You slather it on somebody and you let it cure. It takes a couple minutes. Now you only have a little bit of time to work with that, but outside of that, there's also, you can squirt somebody with a coating of body safe silicone. You only need, a few millimeters of it to get their skin texture and stuff. And then you back that with essentially plaster bandages. And so all that material is cheap. You can buy it on Amazon. I can show somebody how to use it. What it takes is patience. You need somebody that'll actually sit there, in whatever position and however level of nakedness you need in order to get that done. Now, the other way to go about it, there are companies out there specifically. I had a student that worked for one where you step into essentially a photo booth that has 1 million cameras all around you. And they say, smile, and they hit the button and it takes, 100 pictures of you from every different angle, and then algorithmically creates a 3D model of that person. And then you could machine or print out, that model from there. So that works great if you want clothed action figures or anything like that, because it will pick up all that detail, the color, everything. Whereas the, physical molding kind of limits you to what you can do, but is a lot cheaper and easier.
Super exciting. I wouldn't have thought going to Rapid Tech would have like fulfilled that. I just thought, oh, this art school doesn't have what I would need to do what I thought. But how interesting. So very cool. Thank you.
All right.
I like it. Well, Benjamin, this has been incredibly helpful. I really appreciate your thoughts on this. I'm going to let everyone give you a big round of applause virtually through loud claps, whatever seems to be good. But this was very helpful. I learn a ton every time I hear you speak. So I really appreciate it. And it seems like it keeps getting better and better and better. what's available. And again, this is part of one of the real benefits of being at UCI, right? Is beyond just the classroom education that we get. Resources like this are available on campus, and it's a rarity to find this level of expertise, one, and equipment, two. So we're very blessed to have this kind of opportunity. So thank you again, Benjamin, for walking us through it. And again, there's resources if you do need access to prototyping and a budget's a constraint of some sort. It's not an endless budget opportunity, but there is some money. You just have to send me an email and we'll figure out how to push through that. So let me wrap this up. I fixed your name to Benjamin on here.
Sure.
But let me move forward here with next steps for you. The intent to enter, I think everyone has done this at this point, but it's still available for you. There is a workshop in 2 weeks. So we're taking a week off. I hear there's some things going on with final or midterms and that sort of things. But really the biggest one for us was giving us a week to look through the judging and share with your friends. Of course, keep up to date on things. And as a reminder, we've pushed this product spec due date by several days because some people are having trouble with Google Forms. And of course, you're welcome to schedule some office hours with me or with, we can get a judge or a coach to give you a hand with that. And of course, we want you to get started. That's an important element. So thank you to Benjamin. Thank you to all of you. I'd like to see if we can move this over to a new venue. If you haven't done this, it's kind of a fun thing. We tried it last week and we had a blast and we were able to make some great connections. But head over, if you would, to this link. We're going to network. We'll hang out as long as everyone would like to. I've put the link in the chat window there for you. So we're excited to offer that opportunity for you guys to get to know each other a little bit better and have a bit of fun with that. So with that, if there aren't any questions, I invite you to head out and we'll see you over on the wonder.me side. I'll hang out for a minute here just to answer any questions, but thank you everyone. And we'll see you at the next workshop.